Welcome again to Engineers Newsletter Live. I'm Jeannie Harshaw from Trane's System and Application Engineering Group, and today we'll discuss ASHRAE Standard 62.1. This course is approved by the U.S. Green Building Council for 2 Green Building Certification Institute continuing education hours toward the LEED Credential Maintenance Program. After attending today's program, LEED professionals should submit their hours to GBCI. Today's program is also registered with the American Institute of Architects Continuing Education System and qualifies for Health, Safety, and Welfare and Sustainable Design Credit. AIA members, please provide your member number to your local host before leaving today's session. And professional engineers, check your state's rules to see if credit for attending today's program can be applied to engineers' continuing education requirements. ASHRAE Standard 62.1 is titled Ventilation for Acceptable Indoor Air Quality. It specifies ventilation rates as well as system design, construction, and operating requirements that will provide acceptable indoor air quality. It's the basis for many local building codes and is a prerequisite for LEED certification. During today's program, Trane Applications engineers Dennis Stanke, Paul Solberg, and John Murphy will take us through a discussion of the requirements of Standard 62.1, with specific focus on the ventilation rate procedure for calculating ventilation requirements. Dennis, who is a longtime member and recent chair of the Standard 62 Committee, will start us off with an overview of this standard. Then the guys will step us through how to use the ventilation rate procedure to determine the ventilation requirement for each zone and how much outdoor air must be brought in at the system level intake. And later, Paul and Dennis will touch on exhaust requirements and discuss various dynamic reset strategies for saving energy required to condition this ventilation air. Since there's so much that could be covered on this topic, we've done something a little bit different for today's program. We recorded supplemental content that will not be aired during the main program, kind of like a bonus feature. We'll make mention of them throughout the program. This supplemental material is included on the DVD, or it can be viewed on demand at our website, trane.com/ENL. Now for the main program. Dennis, go ahead and get us started.
Okay, first I want to thank all of you for watching these presentations. We've been doing them for many years, and I hope that you find them of value. I don't know how many of these I've been involved with, but I'm happy to say that this is my last one. So in case I forget to say it later, I've enjoyed talking to you periodically, and I hope that you continue to attend long after I've retired to New Orleans, for example. Anyway, today I'm going to give you a quick overview of the 2010 version of Standard 62.1. It's a mandatory language ASHRAE design standard with the purpose of specifying minimum ventilation rates which will provide acceptable indoor air quality and minimize adverse health effects. It applies to commercial, institutional, and high-rise residential buildings, but not to healthcare. Its requirements are organized in sections as follows: outdoor air quality assessment in Section 4, provisions for systems and equipment in Section 5, ventilation rates and calculation procedures in Section 6, construction and startup requirements in Section 7, and finally, operation and maintenance requirements in Section 8. Normative Appendix A, which expands on Section 6 requirements, is also part of the standard. The standard is written in mandatory language so that it can be easily adopted by codes and can be used as a solid technical reference document for other standards, for energy labels, and for building rating systems. This diagram attempts to show how the standard fits. First, here's Standard 62 broken down by section. Traditionally, Section 6 is most important for the model mechanical codes and many local building codes. Its ventilation rates and procedures appear in over 11,000 code jurisdictions. To comply with ASHRAE Standard 189.1, the High Performance Building Standard, building designs must meet virtually all Standard 62 requirements. And the International Green Construction Code allows Standard 189.1 as a project compliance option. Projects following this option include all Standard 62 requirements referenced in the Standard 189.1 document. Some building owners want to pursue a building energy label, like Energy Star or the ASHRAE Building Energy Quotient label. To comply with the Energy Star, all 62 requirements must be met. And since the ASHRAE BEQ label requires Energy Star compliance, again, all 62 requirements must be met. And of course, many building projects these days seek LEED certification. The first LEED indoor environmental quality prerequisite requires compliance with the provisions in sections 4 through 7 of Standard 62.1. So you can see this ventilation standard provides the basis for building codes, energy labels, and building rating systems. Okay, back to the standard to give you that quick overview that I promised. Section 4 addresses outdoor air quality. It requires designers to consider potential outdoor contaminants both in the region and immediate vicinity of the building site. Section 5 covers a broad range of requirements for ventilation systems and equipment. When met, these requirements should help to establish a baseline for building contaminant emissions so that the prescribed ventilation rates and procedures in Section 6 can actually be expected to work. These sections cover a lot of ground, so we've included them in the supplemental material since we want to focus on Section 6 today. Turning now to the procedures for finding design ventilation requirements in Section 6, the standard includes 3 alternative design procedures for finding minimum outdoor airflow rates: the ventilation rate procedure, the IEQ procedure, and the natural ventilation procedure. And it includes exhaust airflow requirements in a separate section because they apply regardless of the design procedure used to determine the minimum outdoor airflow rates. The ventilation rate procedure is most widely used. It prescribes zone-level outdoor airflow rates in a table, and it prescribes equations and calculation procedures needed to find both zone and system-level rates. Most designers understand it and use it, and it's the basis for mechanical codes. Of course, it has a few tricky spots, so we'll go over an example a little bit later. Next is the indoor air quality procedure. Designers find minimum zone and system intake rates based on contaminant levels and subjective evaluation, proceeding as follows. First, identify all contaminants and mixtures of concern, sources and source strengths, and target contaminant and mixture concentrations. Second, use mass balance equations, accounting for any air cleaning devices, to find the zone and intake rates needed to control contaminant levels to less than or equal to the target concentrations. Third, in the completed building, use a subjective evaluation in each zone to find zone and intake rates that satisfy occupants, or use the rates found by subjective evaluation in a substantially similar zone in an existing building. Finally, compare the zone and intake rates found using the mass balance approach to those found using the subjective evaluation approach, and use the larger of these rates. Designers must perform both a mass balance analysis and a subjective evaluation to comply with the IEQ procedure. This requires a lot of work, a lot of judgment, and risk, not to mention a variance in from most code authorities. That's why very few one-of-a-kind building designers pursue it, why Standard 189.1 doesn't allow it, and why LEED has traditionally not allowed it. It's probably best suited for buildings with repeated identical designs, like retail chain stores. I recently wrote an ASHRAE journal article about the IEQ procedure, showing in detail how it might be met. We included a reference to this article in the bibliography, but we're not discussing it in detail today. Finally, the natural ventilation procedure provides for passive ventilation using only natural forces to move outdoor air through the zone. It requires that any natural ventilation system also include a mechanical system designed using either the ventilation rate procedure or the IEQ procedure. A mechanical system is needed to provide outdoor air during those times when the local openings must be closed. To comply, first find how far outdoor air can be expected to penetrate into the occupied zone. This depends on the location of openings and the ceiling height. Next, find the area of the outdoor opening. It must be no less than 4% of the naturally ventilated floor area. Finally, provide readily accessible means for occupants to adjust the outdoor openings and provide controls to coordinate the operation of natural and mechanical ventilation systems. Mixed mode ventilation is required because virtually all naturally ventilated buildings need mechanical ventilation at some point. For example, occupants may close local openings due to rain, wind, heat, cold, outdoor pollution, outdoor noise, and so on. As with the IEQ procedure, we're not discussing the natural ventilation procedure in any detail today. Today, we're focused on the ventilation rate procedure. It covers outdoor air treatment, zone level and system level outdoor airflow calculations, an optional averaging approach to design for varying operating conditions, and an optional control approach to reset outdoor airflow dynamically. Before we turn our attention to ventilation calculations, however, I want to briefly discuss outdoor air treatment. We use outdoor air to dilute and remove indoor contaminants. But since outdoor air itself can contain contaminants, in some geographical locations, the standard requires outdoor air cleaning between the intake and the occupied zone. The ventilation rate procedure requires filters in PM10 non-attainment areas, those areas where the concentration of particulate matter, 10 microns and smaller, exceeds the National Ambient Air Quality Standard. Here's the latest EPA map for PM10 non-attainment areas. At least MERV 6 filters are required for buildings in all shaded locations shown in both yellow and red. This shouldn't be a big problem since the air handler probably has a cooling coil with a wet surface, and Section 5 already requires a MERV 6 filter upstream of any wet surface device. The ventilation rate procedure also requires filters in PM 2.5 non-attainment areas, those areas where the concentration of particulate matter, 2.5 microns and smaller, exceeds the national standard. Here's the latest EPA map for PM 2.5 non-attainment areas. At least MERV 11 filters are required for systems in the shaded locations. Air handler fans must be selected to provide the required airflow whether the filter is clean or dirty. Finally, the ventilation rate procedure requires 40% efficient ozone air cleaners in non-attainment areas where the average daily maximum 8-hour ozone levels are very high, above 0.107 parts per million. Here's the latest EPA map for ozone non-attainment areas. According to Appendix E, only buildings in Riverside, Kern, Los Angeles, and San Bernardino County in California need ozone air cleaners. But these designations change, so designers should check the EPA 8-hour ozone status for any planned building site. Buildings located in ozone non-attainment areas other than Southern California don't need air cleaners to meet Standard 62, but designers might want to consider using them anyway. After all, breathing ozone is harmful, and besides that, if you're designing a high-performance building, Standard 189.1 requires 40% efficient ozone air cleaners in all ozone non-attainment areas, which includes most of California and many major metropolitan areas throughout the U.S.
As Dennis mentioned, we're only going to focus on the ventilation rate procedure for today's program. This procedure includes both zone calculations and system calculations.